Let's continue looking at some basic area concepts. So in the last video, we looked at this idea of a rectangle area, or just area in general, just seeing how many little unit squares we could put in here and tile this. And it's pretty clear to see if you can break this into integer lengths on the side with a certain number of rows and columns that you're just counting there. So if you have like 4 rows and say 5 columns, you can see that you got 4 times 5, 4 groups of 5 added together gives us 20 squares. Now, if we extend this by another half, we found that the area's formula still works. So we have a general formula for a rectangle is just a side length times another side length, base times height. So we looked at that earlier. Okay, now let's look at a parallelogram. So here we have a parallelogram, and the question is, well, first of all, what do we know about a parallelogram? We know lots of things, like by definition, opposite sides are parallel, but we also, by proposition, opposite sides are congruent as well. So here we have this. So how can we get an area formula for a parallelogram, given that we only know so far the area formula for a rectangle? What we want to do is find a rectangle that has the same area as this particular parallelogram. Okay, well, I think you probably know how to do this. You just make a rectangle like this. It has the same base, one of the sides, and then you go up perpendicular to that to make a rectangle. And we want to claim that this red rectangle AFED has the same area as the parallelogram ABCD. Well, they have a lot of this area. This right trapezoid ABED is the part where they overlap. So that area is the same. So we want to basically decompose this. We want to show that basically we can take this, depending on which way you want to think of it, cut off this piece that sticks out on the parallelogram and slide it over here, turn it into a rectangle, or alternately, take this little piece off the rectangle, slide over here, turn it into a parallelogram. Okay, so now how can we do this? Well, we have to prove that these are the same. So basically the area, if it's true, then we have the area is this base times this distance here, which is this time is not, it's the height of the rectangle, and we'll call that the height of the parallelogram, the distance between these two parallel sides, when you're thinking one of them as being the base. Well, we basically want to take this triangle right here and just slide it over. Look at that, it's congruent, right? It's a congruent triangle. So how do we prove it's a congruent triangle? If we can prove it's a congruent triangle, then we know congruent triangles have the same area. That's part of our area postulate. Well, let's see. Well, we know this distance here is the same. The height here and height here are the same because they're um, opposite sides of a rectangle, which we know are congruent. We know we have a right angle here and here. And we know we've got the hypotenuse here, this side here, and this side here parallel and congruent because it's a parallelogram. That's enough. That's side-side angle. That's not normally enough, but if you know this big side is the longest side, that's big S, little sa, or hypotenuse leg of a right triangle, yeah, we know that those are actually congruent, and that's enough to finish out the proof. So here's the whole proof written out. And so that gives us a formula now that for a parallelogram, all we have to do is to take to find the area is to take the base, that distance there, length of one of the sides, times the height, which is the distance perpendicular from there to the opposite side, the perpendicular side. So it's the distance between those two parallel sides. It's the same all the way across. So base times height is our nice little formula for a parallelogram. Okay, let's do another one. How about the area of a triangle. Okay, can we get the area of a triangle? So here we have just any triangle, not necessarily a right triangle, just any old triangle here. How can we find an area of this? Well, what do we have so far? Well, we have parallelograms and we have rectangles. So we could either find a parallelogram or a rectangle that has the same area, or maybe a related area, and then we could use that. Any ideas? Well, one thing we could do is we could turn this into a parallelogram by just creating some extra sides here. Do a parallel line parallel to side AB and a parallel line parallel to the side AC, find out where they meet at D, and now we've got quadrilateral ACDB is a parallelogram. Oh, wait a minute, we know that it's this base here from A to B times this height here. Oh, that's the area of that parallelogram. We just proved that. Okay, well, notice that this trapezoid now is half of that. One of the things that we proved about parallelograms is if we take one of the diagonals, then these two triangles formed are congruent. We already proved that, so don't necessarily have to do that again. And that's enough to tell us that these two areas add up to the area of the parallelogram, but these two areas are the same. So that triangle is half the area of the parallelogram. Well, the area of the parallelogram is base times height, and so the area of the triangle is 1/2 of that. Now we should also be able to see this as an area of a rectangle. And there's the rectangle that has the same area as the parallelogram, the way we did it before by moving that across. We could have actually done this by not even mentioning the parallelogram and found out this here. The trick here is to break this into two triangles here, and then look at the rectangle and to say this triangle, actually we got 4 right triangles here. These 2 right triangles are congruent, and these 2 are congruent here. You'd have to prove this. Let's see, these have a hypotenuse in common. They have a vertical, well, opposite sides in common here. And this is a rectangle across here. FC, whatever that is, A is a rectangle. So we know lots of things about that. Opposite sides are congruent here. So side angle side or side side side. There's a lot of different ways we could get these to be congruent. And same way here. And so that would also do it as well. Now you got to make sure you got to be a little careful. Okay, what if you put it over here? Got to make sure your proof works no matter what. Well, here's your rectangle now. Okay, now it's maybe not so obvious, right? That this triangle is half the area of that rectangle. So that's really not as good of a proof. Works fine when this point where C goes down to this line going through A and B. That's called an altitude. And so if that altitude is lands in the between A and B, this little picture works out really nicely. But if C's out here somewhere, it's a little harder to see, okay? But it does turn out that this parallelogram situation is quite a bit easier to see. You know what? We better look back at the parallelogram situation. Let's see. Can we always have that same, can we always get that rectangle? No matter where the parallelogram is. Yeah, the parallelogram might actually be a rectangle at some point there. What if we get, oh, here, this was a little harder to see right here. Okay, we got this case. So we need to consider this case as well. All right, this is a little bit harder to see because it doesn't decompose just as nicely. That one's not bad. But when you go over here, now it's a little bit harder to see that this is the same area as this rectangle. So we have to be a little bit careful with our proof. So you got to make sure the proof works no matter what. I think it does, though. Let's look here. We have to just be a little bit more careful. Again, we can look at this triangle right here and notice that if you take this and slide it across here, you still get a congruent triangle. So that area and that area are the same. You can see it. So it still works there. And so what do we get for the area of the rectangle? Well, the area of the rectangle, let's do it first. It's the area of this triangle plus the area of this triangle down here minus the area of this little bitty triangle. Well, if we move it over here, we get the same setup. The area of the parallelogram is the area of this one down here plus the area of this shape here. I guess that's a trapezoid. And then minus the area of that little rectangle, little triangle right there. And so still you can get it. You have to be a little careful though that you're actually covering all of the cases when you write your proof up. I may have neglected a case here. Okay, so in the end it still turns out to be the same there. So ultimately, once you get the parallelogram, I think the parallelogram proof is the easiest one to use rather than the rectangle proof over here, although we could probably still make the rectangle proof work as well. I think ultimately we want to make the use the parallelogram proof here. All right, well anyway, we get formulas. The area for a parallelogram then is just base times height. And the area of a triangle is a half of that, so it's 1/2 base times height. Now the height is the distance from one, you take any side to be the base, and then you take the other point and then go down perpendicular to the line containing this. And that's going to be the length, that's called an altitude. The line segment is called an altitude. Its length is called the height of the triangle. All right, the next one video we're going to look at is trapezoids, and there's kind of a lot of interesting ways you can go at looking at the area of a trapezoid. We'll make a whole video on just that one.